Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Shahid Latif, Associate Professor at Department of Computer Science, Sarhad University, Peshawar. Today we will learn the very first lecture from the course of Computer Architecture. The course code for Computer Architecture is CS252 and this course is offered for various programs including BS Computer Science, BS Software Engineering, BS Telecommunication, BS Electronics and even BTech Electrical and Electronics program. Remember that Computer Architecture course at this level is 3-0 credit hour course. It means that we have to cover 3 hour theory per week while there is no lab work requirement for this course. Today we will introduce the course of a computer architecture and will discuss some important terms or topics from the prerequisite for this course. We will start our lecture by discussing the course description. In other words, we will describe the course of computer architecture. Then we will move towards the course outlines. Here we will discuss the tentative topics which we have to cover in this course. Then after discussing the course outlines, we will discuss the grading policy for this course, or in other words, the marks distribution which we will use at the end of the semester for various sections of this course. After discussing the grading policy, we will discuss the recommended books for this course, including both the textbook as well as the reference books. After discussing the books, we will discuss the detailed objectives of this course which we have achieved throughout the semester. At the end of this lecture, we will discuss the prerequisite courses required for the course of computer architecture. These prerequisite courses or review of these prerequisite courses will help us to understand the computer architecture course easily. Some important topics from the prerequisite courses such that the number system, the data formats, the microprocessor architecture in general and specifically 8086 microprocessor, the general buses, the memory management system, the instruction set, the addressing modes, and the pin diagram or pin configuration of the IC of a microprocessor will be discussed as the prerequisite topics. So starting with the course description, remember that the computer architecture course is designed to familiarize the students with the architecture and the organization of any computer system. Remember that computer architecture course is built on the already acquired knowledge of 3 different courses: the digital logic design, the basic electronics, the microprocessor architecture and assembly language. If you have sufficient knowledge of these 3 courses, it will be very easy to understand the computer architecture course. The tentative course outlines for computer architecture include history and evolution of a computers. It means that we will start our computer architecture course by discussing the history of a computer system and the evolution made in improving the architecture and the organization of the computer systems. In this course, we will also discuss the data paths, simply known as the data buses, and the design requirement of these data paths. After that, the memory management or the memory system used in our computer systems will be discussed in detail. which can be classified in three different types, that is the internal memory, the main memory, and the external memories. After discussing the memory and the management or the organization of a memory system, we will discuss another important component of a computer system known as the input or output devices, or simply internal and the external devices. We will also discuss the architectural requirement for the internal and external devices which we are using in our computer system. Another important section named as ALU or ALUs, the abbreviation of ALU is Arithmetic Logic Unit, will be also discussed in this course. To improve the performance of a computer system, a pipelining mechanism or method is used. So we will also discuss in detail the pipelining and the types of pipelining which we are using for the improvement or for the improving the performance of a computer system. The control mechanism or the control section or the control unit of any computer system will be also discussed in this course. Similarly, another important approach which we are using in our modern processors or computer systems, the parallel processing, will be also discussed later on in this course. There are much more topics which we have to discuss in this course, but due to the lack of time and space, we cannot discuss all of these. The grading policy for this course is such that a midterm exam will be conducted, weighting 25 to 30% of the total marks. Similarly, a final term examination will be conducted, comprising 50% of the total marks. As a sessional marks, assignments and quizzes will be taken. Minimum 4 assignments and 4 quizzes will be conducted, comprising the 20 to 25% of the total marks. Recommended books for this course include The Computer Organization and Architecture, authored by William Stallings. We are using 8th edition of this book. If you have any latest edition or even an older edition, it is also acceptable. The second book for this course is Computer System Architecture, authored by Morris Mano. And the third book is Computer Architecture and Organization, authored by John P. Hayes. These three are the recommended books for this course. But you will see that majority of the contents of this course are taken from the Computer Organization and Architecture, authored by William Stallings. So the first book will be used as a textbook or a course book for this course, while the other two books can be used as a reference books for this course. Now the detailed objective of Computer Architecture course are such that we will understand the computer architecture and the computer organization, or you can say that we have to understand, after completing the computer architecture course, the computer architecture and the computer organization and the differences between the computer architecture and the computer organization. We have to overview the history of the computer system and the evolution of a computer system. The third objective of this course is to examine the major components of a computer system and their interconnections, that how these components are interconnected. Similarly, we have to examine the internal and external memory and the input and output devices used in computer system. The fourth objective of this course is to examine the internal architecture and the organization of the microprocessor used in our computer system. Here we will learn the computer arithmetic, the instruction set used for programming, the addressing modes, the reduced instruction set computer are simply the RISC architecture and the CISC architecture as well, and the superscalar approaches. The fifth objective of this course is to examine the internal structure of the control unit or the control section used in any computer system and the use of a microprogramming concept. Similarly, the sixth, the last but not the least objective of this course is to deal with the parallel organization and the multi-core architecture. Prerequisite for the course of a computer architecture: the knowledge of those courses which are required for the better understanding of the current course, the computer architecture. These prerequisite courses include the digital logic design, also known as a computer logic design, the basic electronics, which can be classified in various programs by electronics 1 and electronics 2, and the third one is a microprocessor architecture and the assembly language. So if you have sufficient knowledge of all these three courses, it will be very easy to understand the computer architecture course. Now some important topics from the prerequisite courses such as number system will be discussed over here. You all are very much familiar with the number system which we are using in any computer system. For example, the binary. Here the word bi stands for 2, so it means that such number system which has only two valid digits known as a bits, the 0 and the 1. The other important number system is octal. Octa stands for 8, so that number system which has only 8 digits or valid digits to represent any number smaller or greater. These numbers are 0, 1, 2, 3, 4, 5, 6 and 7. So any number smaller or greater will be made or represented using these 8 digits. The decimal number system, deci stands for 10, so such number system which has 10 valid digits starting with 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9 up to 9. So 0 up to 9, these are the 10 digits. Decimal number system is that system which we are using in our daily life calculations. And the fourth one is the hexadecimal number system, which is also known as an alphanumeric number system. Hexa means 6 and deci stands for 10, so that number system has 16 valid digits or 16 numbers to represent any number in hexadecimal number system. As we know that in decimal number system we have 10 digits. The 11th digit, which is 10, is actually a combination of 1 and 0, or you can say that in 10 the 1 and 0 are combined to form a new digit. To represent these numbers above 9, which are 10, 11, 12, 13, 14 and 15, alphabets are used, that is A for the number 10, B for 11, C for 12, D for 13, E for 14, and F for 15. That's why this number system is known as a alphanumeric number system. Alpha means some alphabets, numeric means numerical numbers. So we have 0 to 9, 10 digits, while A to F 6 alphabets. So collectively, these 16 digits will make any numbers of the hexadecimal number system. Now the data formats. The important or the common data formats used in any computer system include the ASCII. ASCII stands for American Standard Code for Information Interchange. Here, each alphanumeric character, alphanumeric means any alphabet or any number or any other character which we are using in our daily routine, can be represented by a 7-bit code. 7-bit is representing 7 binary bits. For example, to represent a letter B, capital letter B, a binary number of a 7-bit 0101010 is used, which is equal to 42 of the decimal. Similarly, for the character question mark, a binary number is used which equivalent is 3F in hexadecimal. If we convert the 3F into binary numbers, so that 7 bits will represent or will be used for the representation of the question mark. Similarly, for the symbol of @ a decimal or hexadecimal number 40 is used. The other important format is binary coded decimal. It sounds like a decimal number has been coded into a binary number. Here you can see that we have 10 digits in decimal number system starting with 0 and up to 9. So if we write the equivalent number of all these digits in binary, that is 4 zeros for 0, 0001 for 1, similarly 0010 for 2, and so on, 1001 for the 9. So here we can say that we have coded the decimal numbers into a binary. The third important data format is the signed and unsigned data or integers. As its name reveals, signed numbers or signed integers are those integers where the sign is used. It means that the number can either a positive number or a negative number. Here the leftmost bit, simply known as a most significant bit of that number, represents the sign bit of the number, as well as a weight of a -128. If you can see that we have taken over here 8 bits. So it means that the MSB or the leftmost bit of this number is the sign bit, as well as it represents a weight of a 128. For example, in ATH, the MSB might have a value of a 128 if we are dealing with the unsigned numbers. And in the same ATH, The MSB might have a value of a minus 128 if we are dealing with the signed number. So signed number are those numbers which have positive or negative sign, or which can be positive or negative numbers, while the unsigned integers are those which are the natural numbers, or you can say that which are always positive numbers. The basic or the general architecture of a microprocessor is shown over here. Here we can define the general architecture of any device or of any system such that the arrangement of various devices or components in a complete system or a network. For example, the general purpose processor with its basic architecture is shown over here. It comprises arithmetic logic unit, the register array, the control unit, and many other devices. Now, specifically, the architecture of a 8086 microprocessor can be divided into two sections: the execution unit and the bus interface unit. These two sections include arithmetic logic unit, the registers, in which some registers are general purpose registers while some are special purpose registers, the instruction queue, the buses like data buses or data paths, the control bus and the address bus, and the operating system. So this is the architecture of a 8086 microprocessor, or you can say that that is the block diagram of the architecture of a 8086 microprocessor. The general buses used in any microprocessor, specifically in 8086, are the data bus, the control bus, and the address bus. These three are the general buses used in any computer system. In case of 8086 microprocessor, the size of data bus is 16 bits, or you can say that the data bus of 8086 is 16 bits wider. The size of the control bus is 16 bits, or the control bus has 16 data paths. The address bus is made of a 20 data paths, or you can say that 20 bits address bus is used in 8086 microprocessor. These three type of buses are commonly known as a system bus. The memory management in any microprocessor, along with the mapped I/O, is shown in this figure. Here you can see that a memory space is used. That memory is divided into locations. You can see that that is the very first location of that memory, that is the second location, and so on. That is the last location of this memory. These locations are equal in size. Each location has a unique address in order to distinguish from the other locations. Here you can say that the starting address of the very first location is 20 bits of binary, which can be represented by 5 digits in hexadecimal. Actually, that is 20 bits of a binary number. Similarly, the second address of the second memory location has an address of a 0001 in hexadecimal number system, or you can say that 20 bits with LSB as a 1 in binary number system. So here you can see that each location has a unique address. A portion of this memory is mapped for the I/O devices. It means that this portion of the memory is reserved for use of the I/O devices. That's why it is termed as the I/O port addresses, or simply the I/O addresses. Here you can see that each location is representing the address of a port or the address of a input or output device, starting with port 0, the port 1, port 2, port 3 and so on up to 4095 are combined the 4 kilo locations or 4 kilo devices. The addressable memory, here we are going to learn the address lines and the addressable memory. Remember that 20 address lines can address 1 megabyte of memory or 1 mega locations if the size of each location is equal to 8 bits or 1 byte. Similarly, the 32 gigabyte memory can be addressed using 35 address lines. How we will know that a 1 megabyte memory or more than 1 megabyte memory or lesser than 1 megabyte memory will be addresses using how much address lines? So we have a power of a 2. If you can see that the 2 power 0 is representing 1. Similarly, the 2 power 1 is representing 2. It means that if we have one binary bit, so the two combinations are possible. If we double the number of binary bits, means that if we are using the 2 binary bits like 0 and 0, so we have only 4 combinations. The unique combinations or the possible unique combinations is equal to 4. That is 0 0, 0 1, 1 0 and finally the 1 1. By including another binary bit, we will have 8 different combinations. In similar fashion, if we increase the number of binary bits in the power of 2, we will have a larger number of different or unique combinations. For example, in case we have used 10 binary bits, so we will have or we will be able to address 1024 different locations of a memory. For the simplicity, this 1024 can be represented as a 1K or 1 kilo. If we increase another binary bit, so the combinations will be doubled and we will have 2 kilo addressable locations. By increasing the number of bits, when we reached to the 20 bits, so here we will have 1024 multiplied by 1024 unique addresses or unique combinations of the binary numbers. That 1 kilo is representing 10 power 3. So multiplying the 1 kilo with 1 kilo, we will have 1 million, or in other words it can be termed as a 1 mega. So to address the 1 mega locations, the size of location does not matter. It might be 8-bit or it might be 16-bit and so on. Remember that to address 1 mega or 1 million locations, we must have used 20-bit addresses. Similarly, to address 2 million or 2 mega locations, we have to use the 21 binary bits, or the address will be 21 binary bits for each location. If we increase the binary bits to 30 bits, so we can say that now we can address the 1 giga locations, 1 gigabytes or 1 giga words of any memory system and so on. Now the instruction set. If you remember, 8086 microprocessor has more than 100 instructions, while the variation of these instructions exceeds even the number of 20,000. So for the simplicity, these all instructions are classified in various groups. There were used 6 groups. The first group include all those instructions which are used for the moving or the movement of a data or the transfer of a data. So that's why they got the name of a data transfer instructions group. For example, the move instruction, the push and pop instruction used with the stack memory, the in and out instruction which are used with the IO devices, etc., etc. The second group of the instruction set is that group which has all those instructions used for the arithmetical or mathematical operations. For example, addition, subtraction, multiplication, division, increment and decrement, etc., etc. The third group is the logic or bit manipulated instructions, are those instructions which are used for the logical operation or for the bitwise operation. For example, the AND operation, the OR operation. AND is logical multiplication, OR is logical addition, the XOR for comparison, the NOT for the inversion, the compare or the complement, the shift and rotate instructions, etc., etc. The fourth group is the string manipulated instructions. It means that this group of instructions include all those instructions which are working or which are used for the working with the strings of data. For example, move s is representing or used for the transfer of a string of data. Similarly, load s, store s or stored string, compare string and the scan string, etc., etc. The fifth group of the 8086 instruction set is the program control instructions. It means that all those instructions which are used for the controlling of a program or for the controlling of the sequence of the instructions or for controlling the order of the execution of the program or instructions. These instructions include the jump instruction, the conditional and unconditional jump instructions. Similarly, the conditional and unconditional call instructions and the return instructions which are used with the subroutines. The sixth group of 8086 instruction set is machine control instructions, are all those instructions which are used for the control of the machine, for the control of the processor. For example, NOP stands for no operation, the wait instruction, the halt instruction, etc., etc. The addressing modes. Every computer system is using different types and different number of addressing modes. In case of 8086 microprocessor, you have learned that 8086 microprocessor is using 7 different addressing modes. Here all these addressing modes with their examples are shown. The first addressing mode is register addressing mode. Remember that addressing modes are the ways in which the addresses are, in which the operands of an instruction can be addressed, or the different ways, the different modes in which the operands used in any instruction can be addressed. The first one is register addressing mode. Here you can see that we have an instruction which has a opcode of a move, and the operands, the source operand and the destination operand include AX, the accumulator, and BX, the base register. According to this instruction, the contents of a BX register will be transferred into AX register. So here the two operands, the source operand and the destination operands, are used. Now we are addressing these two operands using the registers of a microprocessor. That's why it's got the name of a register addressing mode, or that is the one way of addressing the operands, by using the registers of the microprocessor. Similarly, the next addressing mode is the immediate addressing mode. Here, according to this instruction, the 1, 2, 3, 4H is a value. It is a direct number, a hexadecimal number, and we have to transfer this number into the accumulator register, the AX. So that type of addressing modes where the one operand is a direct value or a number is termed as a immediate addressing mode. Similarly, the direct addressing mode is that addressing mode in which we are using the memory addresses directly. The brackets are representing the address of the memory location, and the address is 0345H, means that now 0345H is not a number, but it is representing the address of the memory location. So according to this instruction, the contents of a AX register will be transferred to a memory location addressed by 0345H. The register indirect addressing mode, that addressing mode in which the address of the memory location is not directly given, but it is given or it is covered inside any register, any other register. So according to this instruction, the contents of the CX register will be copied or will be transferred to a memory location addressed by the contents of the BX register. The BX register might have the 0345H, but in previous addressing mode it was directly revealed, while here the contents or the address of the memory location is enveloped into a BX register. The fifth one is the base plus index addressing mode. That type of addressing modes where the address is made of a base register and the index register. Here you can see that the contents of the two registers, the source index and the base registers, are combined to get the address of the memory location. So according to this instruction, the contents of a base pointer register will be transferred to a memory location whose address is the sum of the contents of a BX register and the source index register. The sixth one is register relative addressing mode. Here you can say that a displacement has been shown. So we can say that the address of memory location is the contents of the BX register plus the displacement of a 4. Now the address of the memory location is actually the sum of the contents of the BX register and a number 4. So according to this instruction, after accessing that memory location represented by this address, the contents will be moved or transferred into a CL or the lower byte of the counter register. The seventh addressing mode used in 8086 microprocessor is a base relative plus index addressing mode. Here you can see that base register and the index register along with the relation or the displacement will be used to represent the complete address of the memory location. That is representing the complete address of the memory location. So according to this instruction, the contents of a DX register or simply the data register will be transferred to a memory location which address is made of three different quantities: the contents of a BX register, the contents of a source index register, and the array, the relation or the displacement. The pin diagram of a 8086 microprocessor is shown over here. You know that 8086 microprocessor can be used in two different modes, the minimum mode and the maximum mode. When we are using the external devices like the DMA with the microprocessor or any coprocessor with the general 8086 microprocessor, then we are using our processor in the minimum mode. Here this 8086 processor has a 40 pin IC as shown over here. The pin number 1 is starting from the left of the IC and it ends at the pin number 40 in a U-shaped manner, like over here. Means that the top left is the pin number 1 or starting pin of the IC, while the right top of the IC is the last pin, the 40th pin of the IC. Here arrow has been shown with each pin. Some are pointing out of the IC, some are the bidirectional, and some are the pointing in to the IC. It means that that is the output pin of that IC. The bidirectional pins means the microprocessor can receive and send data or signal on these pins, while the green color incoming or pointing in pins are representing that the microprocessor is receiving data or signal on these pins. The details of these pins or this IC are available in various books as well as on internet, so you can search for the functions of each pin of that IC. Thank you very much. That is all for today, lecture number 1. If you have any question, you can ask me through my email address shahid.csit@soot.edu.pk. Once again, thank you very much.